Hello, this is a chemistry video. I've been following the general order of Brown, LeMay, Burston, and Murphy's chemistry, the central science, and we've just started looking at chapter 7, which is on the periodic properties of the elements. So I've got a nice little periodic table up behind me. The periodic table is arranged in a certain way that highlights the fact that we can group the elements in different ways. They have similar, if you go up and down columns, they behave similarly. If they go across columns, they have certain things in common as well. This particular video is on effective nuclear charge. What in the world are we talking about? What is that effective nuclear charge? The Z factor. What is that all about? Well, we have a complex situation. Let's say I'm an electron. I'm just hanging out here on the outskirts of the atom, whatever atom it is. I'm just an electron out here. Our story begins with an electron, a valence electron. The valence electrons are the outermost electrons because, as you know from chapter 6, electrons there's assigned seats in the atom. Depending on what atom we're talking about, there are assigned seats for the electrons. Well, actually, the seating arrangement is the same for all atoms. We just kind of we line up the electrons, one by one into their seats in a certain order. Must put it in this order. But let's say I'm an electron. I'm out here. I'm on the outskirts of Mr. Atom, and well, what kind of an electric charge do I feel from the nucleus? The nucleus is like the sun of the atom, it's way off down there, but it's exerting a force on me. What kind of a force is the nucleus? What kind of a force is it exerting on me? Well, Mr. Electron out here, it's experiencing an attractive, I don't know whether it's a guy electron or a girl electron or I don't know what the electron is, but he's experiencing or she's experiencing an attraction from the positive nucleus. Okay, we've got a negative electron experiencing opposites attract, right? You have a negative electron out here in the valence land experiencing attraction from the positive nucleus. But then there are other competition. The other electrons, their competition, they like the nucleus too, and so I'm repulsed by those other electrons. So we got Mr. Electron out here, who is both attracted to the far off positive nucleus, protons down there, very attracted to the protons. But I've got this maybe crowd of electrons in between me, and they're pushing me away because they're negative. They're negative, and they're negative Nellies, and they're pushing me away. Okay, so it's a complex situation. You've got a negative electron that is attracted by the nucleus, but repulsed by other electrons. And so what is the effective, the kind of bottom line electric charge that ye old electron is experiencing? What is the effective nuclear charge on a valence electron? Or, I mean, it doesn't have to be a valence electron. We can ask, what is the effective nuclear charge on any electron? And the symbol for that is going to be Z effective, ZF. F stands for effective, and Z stands for the charge coming from the nucleus. All right, Z is the positive charge coming from the nucleus. All right, so what is this effective nuclear charge? Well, it's going to be it's not going to be a simple thing if you want to get precise, but we can generally think of it as how an electron interacts with the average environment created by the nucleus and other electrons. We have we add up the nucleus, the protons, we subtract the electrons, whatever the average, by the time the force gets to Mr. Electron out here, how did it end up? How much of it got through the defensive, field of the electrons in between me and the nucleus? How much of it got through? What is the average environment that was created by the nucleus and other electrons? Well, it's going to be, as we've already implied, it's going to be a little less than just the charge of the nucleus. The nucleus is saying, I want you, electron, I want you, I'm attracted to you. So the nucleus has a certain positive nuclear charge, but the electrons in between are filtering out, are shielding some of that charge. So it's not going to just, so the effective nuclear charge is not just going to be the charge of the nucleus. It's going to be less than the charge of the nucleus because some of it's going to get filtered out. The inner electrons shield or screen Mr. Electron out here, or Miss Electron, I don't know. The negative electron out here is being screened from the positive charge in the nucleus. And so we might just say that the effective nuclear charge on an electron out here is going to be the positive charge of the nucleus minus the screening constant that is caused by the electrons in between the nucleus and Mr. Valence electron or Miss Valence electron out here, okay? So S is the screening constant. The effective nuclear charge that an electron out here experiences is going to be the charge of the nucleus minus the screening effect of the intervening electrons, okay? So there are some trends in the periodic table. What's this chapter on? Periodic properties of the elements, right? So there are going to be some trends in the periodic table. So the value of the screening constant is going to be usually close to the number of core electrons in an atom. So it's almost going to be like, well, this is what we're going to do just for simplicity. The positive charge of the nucleus minus the number of protons as a positive minus the number of intervening electrons as a negative. S is going to be more or less, we're going to at least start with saying that the screening is the number of electrons. So number of protons minus number of intervening electrons gives us the effective nuclear charge on a valence electron. Now, the orbital position of that electron has an effect too, because as you know from chapter 6, electrons aren't really particles. They're a probability distribution wave. Well, I mean, they're particles and wave. Anyway, who knows? That's the big quantum question, isn't it? But the probability distribution that we call an electron forms different shapes. So for the ones that are in the first two columns, the first two groups, their outer electrons are in a sphere, the s orbital, you know, and so s orbitals relate. They're all about basically the electrons always going to be more or less equidistant from the nucleus. So s orbitals behave in a certain way, or electrons in s orbitals behave in a certain way in relation to the nucleus. The p orbital, you know, is much more of a flowery kind of perpendicular thing, and so the electrons in the p orbital, they relate to the nucleus in a different way. So the orbital position of electron does have an effect. I believe they use sodium as an example. You would expect sodium to have an effective nuclear charge of +1, but it's actually, I think, something more like 2.5. Who knew? But it has to do with the shape of the orbitals, as I recall. Okay, so effective nuclear charge increases as we go from left to right across a period. As we go from the left with like sodium and so forth, potassium, when we go from the left over to the right, we are going to see that the effective nuclear charge increases. And the reason given is that as you get more electrons around, they are less able to screen the charge of the nucleus. They're too busy fighting each other and so more of the attractive force of the nucleus gets through the further you move to the right in a period, in a particular row, okay? If you go down a column, the effective nuclear charge doesn't change as much as, so going horizontally from left to right, it increases significantly, or a bit, at least significantly, let's say. But as you go down, it doesn't increase nearly as much, but it does increase slightly because again, you have more electrons in between and they are fighting with each other and the charge gets through. That's what I'm going to say at least. So these are some of the trends of effective nuclear charge. It gets larger as you go from left to right across a row, across a period. It gets slightly larger, but not as significantly larger as you go down a column, down a group. Well, that's it. This has been a video on effective nuclear charge.